So radicals is just a fancy way of saying root. In fact, radix, which is where we get the word radical from, is just the Latin word for root. Radix just means root. The reason why things are called roots, a square root or a cube root, is that if you think of some line like this and you want to think of it as being the square root of 5, well, this line can generate a square. There's a square that you can put on it like this, and the area of that square is 5, right? Because this is root 5 by root 5, and by definition what a square root is the number that when multiplied by itself gives you the number that's hiding underneath this sign, which by the way is just a lowercase r for root or radix or radical. And so the area of this square is 5. So this is the square and this is the square root. Now some squares, or some numbers I should say, like 16 have nice square roots. 4. 5 has a square root too. It's the square root of 5. It's certainly not a whole number because 2 is too small, because 2 squared is 4, and 3 is too big because 3 squared is 9. But also it's not any fraction. That is, there's no fraction a over b that when you square it gives you 5. And there are several ways of seeing this, but we'll leave that for another time. For the moment we want to see how we can simplify some roots or some radicals and write them in simpler terms. That is, we want to take a root like the square root of 12 and see how really the square root of 12 is made up of several copies of a smaller square root. In particular, we'll see that it's just twice the square root of 3. And why would you want to do this? Well, the square root of 3 is a more familiar object, and thinking of twice that might be easier to conceive of than the square root of 12. It was also in the old days nice from a computational standpoint, where knowing a decimal approximation for the square root of 3, you may not have to look that up at a table, whereas the square root of 12 it would be less familiar. So doing computations by hand, being able to do these kinds of simplifications, was more important than it is today, when I can just take out my calculator and find out what the square root of 12 is. Still in all, it's a useful thing in order to better understand the way that square roots are structured, and they can play a nice role in more algebraic things. So the point here is for us to be able to see why this works and also how it works. So there are two ways of seeing why the square root of 12 is the same as twice the square root of 3. One is a more algebraic way, and the other is a more geometric way. Great. So the algebraic way I feel like lends a little less insight but gets the job done. So you want to see that these two things are the same? Great. Well, let's just square both sides. If I square this side, I get 12. If I square this side, I'll do this carefully. I get 2 root 3 times 2 root 3, which is just 2 times root 3 times 2 times root 3, which I'll write like this, dropping the parentheses because multiplication is associative. So if I scrabble these guys around, because multiplication is commutative, I can say 2 times root 3 times root 3, and by definition that's 3 and that's 4, and so there's our 12. 12 equals 12. So we can see that it works. From a geometric standpoint, consider the following. If I want the square root of 12, then I better start with a square that's 12, area 12. That means this is root 12, and this is root 12. Now consider what I can do with this square whose area is 12. I can chop it up into some smaller squares, like this. Soup. And that's 4 of them. So each of their areas of the smaller squares must be 3. That's 3, that's 3, that's 3, and that's 3, for a grand total of 12. So how long is this? That's root 3. And how long is this? That's root 3. So we can see that this whole thing, on the one hand, is root 12, and on the other hand is clearly twice the square root of 3. Now what was it about 12 that allowed us to do this? If I tried doing the same song and dance up here with 5, if I tried chopping it up into 4 squares, well, each of these individually would be 5/4, clearly. So I guess it would be true that that's the square root of 5/4, and that's the square root of 5/4, and so that the square root of 5 is equal to twice the square root of 5/4. I don't know if I would call that simpler. So what is it about 12 that makes this work out? Well, that it's divisible by 4. And why 4? Well, 4 is a nice square number. So the upshot is, anytime that your square root number, the guy that's sitting under here, can be divided evenly by a perfect square, you can get this sort of nice thing where your original square root is just a multiple of some smaller square root. So let's see a couple of examples. So the square root of 18, I'll draw the picture. So here's a square, it's 18. So this is root 18, and this is root 18. So 18 is not divisible by 4, but it is divisible by another square number, namely 9. So if I chop this up into 9 little squares, each of their areas will be 2. So I'm not going to write them all in, but I will write the ones along the bottom here. This distance and this distance and this distance are each root 2. So we can see that the square root of 18 is equal to 3 times the square root of 2. So the picture is not necessary once you see what's going on. It's certainly helpful. But it's that square factor that really matters. So you can do this in a more arithmetic or algebraic rigmarole. you can skip the picture and jump straight to the heart of things. I can write things like this. Well, root 18 is equal to root 9 times 2, and then I pull the 9 out front and it becomes the 3. So 3 root 2. Right? That's just encapsulating what we talked about there with the picture. We've got the 18. The 18 is really 9 2's. Those 9 2's of area become 3 2's of distance, or 3 root 2's of distance, and there's our 3 root 2. Okay, we'll do one more example, and then we'll call it quits. So let's say the square root of 75. So this time I won't draw the picture, although you can do that on your own. The square root of 75, what's a perfect square that goes into 75? Well, that would be 25. 75 is the square root of 25 times 3. Think about all those 25 squares, the 5 of them lined up along the bottom, so that our answer will be 5 times the square root of 3. Okay, so that's the idea behind being able to take a large number under the radical and being able to see it as a multiple of a smaller number under the radical.